How to calculate partial derivatives, part 2. We continue what we did in the last video by taking a more difficult example. So we take a function f of xy that is defined by an extension to a point. So the function f of xy is equal to x2y over x2 plus y2 for any xy not equal to 0, 0. So we notice very well that this is not defined at the point 0, 0. That's why at the point 0, 0, we will add a value which is the value 0 to complete this function, to fill the hole where this function was not defined. So this function is defined by an extension at the point 0, 0. We would like to study the differentiability and eventually also, before the differentiability, the continuity of this function on all its domain of definition. So to start, we can of course say that this function is defined, differentiable, continuous at any point outside 0, 0. Because at any point outside 0, 0, that's only a rational expression, a fraction of two polynomial expressions in x and y. So these functions are known to be continuous, differentiable at any point where they are defined, at any point of their domain of definition. That's why at any of these points we can calculate the partial derivatives using the usual formulas you already know. So it's a little bit the same thing that we did in the last video, where we just considered that y is a constant with respect to x and we differentiate it with respect to x, and the other way around. So df over dx can be calculated in this way. Y is a constant, x is the variable. We calculate the derivative of this. This is an expression like u over v. So the derivative will be u prime v minus uv prime over v squared. And so you do your formulas and you get the expression. We can also calculate df over dy, and it will give me also this expression. So the complication in this function is not the partial derivatives at a point of the domain of definition. The complication is that we need to calculate, or try to calculate at least, the partial derivatives at the point where the function is extended, at the point 0, 0. In fact, if we need to study the function, its continuity or its partial derivatives at any point of the domain, so we need to partition the domain into all the points where the function is known to be continuous and differentiable, and the points where we have problems, the problematic points. And in this case, 0, 0 is the problematic point. So of course, if we need to study the continuity at the point 0, 0, this is something you can do using the methods we already explained in other videos about the continuity of the function. Now what we need to do in this video is the partial derivative of f with respect to x at the point 0, 0, and the partial derivative of f with respect to y at the point 0, 0. To do this at a point where the function is extended, we need to go back to the definition to use the definition of the partial derivative of f at a point 0, 0. The definition is given like this: df over dx at the point 0, 0 is the limit when h goes to 0 of the rate of change, and I will add an incrementation to the variable to which I'm calculating the derivative. So this is the derivative with respect to x, so it will be limit when h goes to 0 of f of 0 plus h 0 minus f of 0, 0 over h. So now we need to take the expression of f at a point not equal to 0, 0 and use it to calculate f of 0 plus h 0. So we replace x by 0 plus h and y by 0. And then for f of 0, 0, that's equal to 0 by definition of f is equal to 0 when xy is equal to 0, 0. And we calculate the limit of this difference over h. And of course this will give me h squared times 0, which is 0, over h squared plus 0, that's h squared. So 0 over h squared, that's 0, minus 0, that's 0 as well, over h, that's 0. So it's the limit of 0 when h goes to 0, so that's of course equal to 0. So the partial derivative of f with respect to x at the point 0, 0 is equal to 0. We do the same now for the partial derivative of f with respect to y, but this time we'll replace y by 0 plus h to find the incrementation. So it will be f of 0, 0 plus h minus f of 0, 0 over h equals the limit as well of 0, which is equal to 0. Finally, we calculated the partial derivative of f with respect to x and y at points outside 0, 0 and at 0, 0 as well. So we can say that the partial derivative of f with respect to x is equal when xy is not equal to 0, 0 to the expression we found when xy is not equal to 0, 0, and then it's equal to 0 when xy is equal to 0, 0. We do the same for df over dy. Now let me give you a final remark. If we would like to prove that the function f is differentiable, we need to prove, as I said before in the last video, we need to prove more conditions. So we have a theorem in the course that says if you want to prove that a function f is differentiable at a point, you need to prove that the function is C1 in an open neighborhood of this point. So in practice, what does this mean? So you need to take these two expressions, df over dx and df over dy, these two expressions we found at 0, 0 and outside 0, 0, and to prove that these two functions are continuous at the point 0, 0. If you do this, then you can deduce that if they are continuous, of course, you can deduce that the function f is differentiable at the point 0, 0.